course. So this week, first I will make a quick refresher of last week. So remember, an execution is an infinite sequence. Starts with a configuration, and then something happens. New configuration, so you have events. So the events can either be computation events, so a local computation, or a message delivery event, where then a node J receives the message sent by node I. So that we saw last week. So let's go forward. Just give you a refresh of the few important concepts. So we also learned about causality. So events of an execution have some connection to each other. Some of them have to be before or after the others. So we define a relation among all the events, and it's a partial order called causal order. So in the same process, all the events are ordered totally, and if a node produces an event, its message is sent, M, and the message is delivered, then the producer is before the deliverer. And if there's an event that's delivered and consumed by a computation, then also the delivery is before the consumption, and it's a transitive relation. So we saw that last week. We also saw similar executions. So here we have a time-space diagram. So here we have 3 executions that are similar, which means they have the same causal connection between the events, but there's still a permutation, so the total order and time is not the same. But since the causality is preserved, it's actually, they're doing the same thing. So they're called same computation. Okay, so we saw that. And then we saw, very briefly, we saw Lamport and vector clocks, but let me just do a very brief. So we saw 2 ways that execution can figure out its own causality from inside. The Lamport clock, which is a very simple thing, it's just an integer for each node. And the vector clock, which has to store a vector in each node. It's much more information. So the Lamport clock is kind of very weak. If 2 events are related causally, A happened before B, then the Lamport clock will tell you which is earlier. It's not so strong. The vector clock is much stronger because it can tell you if I have 2 events, if you know the vector clocks, you can say whether or not they're causally related. So if they're actually comparable, if you can actually compare the vectors, then there's a causal connection. Okay, so the vector clock is stronger. Okay, now let's start today's lecture. So I want to talk about complexity, so the time or the messages. So we want to see how much work the algorithm has to do. So there's 2 ways to check that, either the number of messages an algorithm uses or the time it takes. Okay, so the algorithm runs, at some point it's terminated, and all the nodes go into terminated states. So all states in a configuration are terminated, and there's no more messages. So that's important. So it's not enough that the nodes are done, but if there's no more messages in the network, the network is empty. Okay, and then the algorithm is terminated. How long does it take? So we can compute that. So we look at all admissible executions. So admissibility, remember, it means the execution is fair. It means all the processes are running, so the executions are infinitely long, which all the processes and all the messages are eventually delivered. This is a new thing, huh? So admissibility is very similar to fairness in concurrent systems, but there's a new thing that, of course, this is new. In a distributed system, you have messages in the network. So if you look at all the executions, all possible executions of the algorithm, you take the maximum. So complexity has to give you the worst case. Okay, in the worst case, some of these might be better, some might be shorter, some might be longer, but you have to be sure it's done, no matter what execution is happening. So we have to take the worst case. So the worst case for all admissible execution is called the message complexity. Okay? And also we can talk about time. So this is a very rough estimation. We're not going to measure the time in seconds, but we're going to measure the time kind of in the natural unit for the system. We're going to assume that messages take a lot of time and local computations are very quick. Okay? So the messages will take 1 unit. So we're going to assume it's 1 unit. We don't know how much in real life, but maybe it's like 10 milliseconds, 1 millisecond, microsecond. But we're going to count it as 1 unit. And the computation event is so fast, we're going to say it's 0. Okay? When we want to count the time complexity. And the message delay, we're going to say at most 1 unit, so it could be 0 or 1. We're going to count this execution, it could be 0 or 1, because message times will fluctuate. Okay? Doing exactly 1 actually is wrong, we'll see later. So at most 1 is much better. So we can time the executions. So we have to figure out this number, which is the time. So each comp event is done at a certain time. So the comp event takes 0 time, but maybe it happens at time 35 or at time 600. The first event happens at time 0, and each process, the time will increase, and it's actually the messages. So if we have a send of the message and a consuming of the message, there can be a time of 1 unit between that. Okay? 0 or 1. So this is the time of the delivery. Huh? So you have a comp which sends the message, then there's a delivery, and then a computation consumes the message after that. And so the delivery can take 0 or 1. So the time complexity is the maximum time for all admissible executions where we compute this time values. Okay? This is actually kind of subtle. It seems to be a very simple thing, but we're going to go through an example here. Okay? It's actually very important that the time for a message is at most 1 and not exactly 1. That it's always exactly the same. Because actually message delays are varying. So we're actually kind of looking at the maximum message delay, and messages can be quicker than that. So here we're going to assume there's 0 or 1. Okay? And we'll see that if you do exactly 1, actually, it's wrong. It's kind of not good. We have to do at most 1. So let me show an example, and it's actually kind of subtle. At most and equal to 1. So the time complexity is the maximum time for all admissible executions when messages take either 0 or 1, at most 1. And not exactly 1. So we're going to compare those two here, because I want you to understand what it means. Okay, you'll see it's kind of a little bit subtle. So here's a simple algorithm. So this is one of the first algorithms you see. So this algorithm is going to do a broadcast. So you have a bunch of nodes. So I can make like there's a graph here with nodes. For example, it looks like this. We have one node, which is the source node, and we want to send a message. We want all of the nodes to get the message. Okay? So we assume that there's n nodes in all, and they're connected in a network. Okay? So here's the algorithm. We send a message A. We want all the messages to receive. We send a message called A to all the neighbors. So the source sends this message A to the neighbor. So here there's two neighbors, huh? And then we run the algorithm, and all the other nodes, they run this code here, the others code. So when the source receives A from a node P, whatever node. If this node receives it from this node, that's the node P. It has a local variable called parent, which starts out to be null. So if parent is null, then we set it to be P. So the parent will be P, if this is P. In this case, it will be the source. And then it forwards A to all neighbors except for parent. Here it goes, it forwards here. And this one is the same. So parent will be source. And it forwards A to all the neighbors. Okay? And except parent, so it's not going to go back. It's only going to go to the ones that didn't get the message from. And then it sends B to the parent. So there's a second message, B. So B is like the acknowledgement that the node received A. Okay? And the source, the B's will all be going back up to the source, and eventually the source will receive n-1 B's. And when it does that, it knows that everybody has received A. So a node, when it receives A, it sends B to the parent. So this node will send a B here to the parent. Okay, it sends a B. And these two B's arrive there. When a node receives B, it just forwards it. Okay? So any node that receives the B, maybe it receives a B from below, it will just forward it back up to the parent. So all the B's eventually go back up to the source. Okay? Now you notice it's actually building kind of a tree here. The first A it receives will make it set the parent. Okay? And then it sets the parent. And that means later on when it receives more B's, the B's will go up to the parent. So this makes sure that all the B's go back up. Okay? We can calculate the time complexity of this algorithm. So it depends on how long the messages take. Okay? So here's a message A. It could take 0 or 1 time unit. Here's another message, 0 or 1. Okay? The B's also 0 or 1. So we have to figure out what is the longest delay with messages where we can pick either 0 or 1. So we can pick it so it takes longer or shorter. We have to find out the longest one. Okay? So we can ask the question, what is the time complexity if every message takes at most 1 time unit, 0 or 1? Okay? And so you can figure it out depending on the graph you have here. The time complexity. So if we have a very simple graph, if we have something like this, then there's going to be an A going down, an A going down, a B up, and a B up. So it'll be 1, 2, 3, 4. Here it'll be 1, 2, 3, 4. And the maximum, you have to take the maximum. The maximum, if they all take 1, 1, 1, 1, 1, then it'll take 4. Both of these are running in parallel. So this is 4, this is 4. So basically the time, the maximum time is going to be 4 in this case. So the time complexity is 4. Here I've chosen all the times exactly 1. But some of them could be 0. Some of these times could be less than 4. If this one takes 0, then this path will be 3, and this one will be 4. But the maximum is still 4. We have to take the maximum. So you can actually figure out both of these. At most 1 time, or exactly 1. It seems intuitively that it's going to be slowest if all the messages are slow, right? The slower all the messages are, like 1 for example, not 0, then the complexity will be slower. But that's not right. That's wrong intuition. Okay? So if you compare the at most or the equal, so assume the messages all take exactly 1, okay? Then we have some executions, right? Now at most 1 can only make it worse, because every execution with exactly 1 is also possible when it's at most. You just pick one. The at most one also allows you one. But the at most model lets some executions take 0. So there's more executions in the at most model. You see that? So the exactly one model has certain executions, but the at most model has executions where you can pick zeros. So it has more executions, strictly more. See, the at most model has strictly more executions than the exactly one. Because here in this pink model, you can have executions with 0 or 1. And here in the exactly one, they're all 1. So here the 0 executions are new ones that are not possible in the green circle. So that means, since we're taking the maximum over all, the at most model, it will never decrease. It can only increase, right? It can only increase. So you might say, well, you know, it's not going to be so important because the at most model, it can only make some messages go faster here. It can only make some messages take 0. So maybe the time complexity will not increase. But that's not true. There, in the example algorithm I showed you, the at most one model actually has strictly greater complexity. So you can have networks where it's actually slower if you can let messages go faster. Okay? Yes?
Could you give an example of that?
Yes, I will give you the intuition. But I will not give an example because the example will be an exercise for you guys. Okay? See, so this is very important. So the complexity is the maximum time over all executions. So it's actually going to be the case that if you allow some messages to go faster, that the time complexity will increase. Okay? So let's take this example, the broadcast example. I'm going to give you some intuition on that, but I want you as an exercise to find the example, okay? To understand. When you find the example, then you will understand what time complexity means, okay? So here's some intuition. So we have these A and these B messages, huh? So the A messages go down, and when they go down, you have these parent nodes which you're calculating. So it's like building a tree structure. So the B messages come back up. So eventually the source node will receive n-1 B messages, okay? So there's no failures in this case. All the nodes have neighbors and they're working well. So the A messages going down take 0 or 1. And let's assume the B takes always 1, but the A is 0 or 1. Okay? If the A's are 0, it goes down. Maybe there's a long path of A's going down. If the A's are all 0, this long path can be very fast, right? If the A's are all 0. But the B path going back up is going to be slow if it's a long path. Huh? See what I'm trying to tell you here? So if you somehow arrange it that you make very long paths going down, then you force the B's to take these long paths going up. Okay? So that's kind of an intuition. So the other way to see it is that in this code, you're actually building a data structure. Each of these nodes is storing the parent node, huh? Is storing a parent. That data structure depends on the speed of the A's. Which one node is it? Like this node, for example, here has 2 parent nodes. So which one is going to be the parent? This left one or the right one? Well, it depends on the speed of the A's. So choosing the speed of the A's, you're actually forcing this parent to be some parent. Maybe you could force the parent to be one, which is going to be very slow for the B's. Okay? So that gives some intuition. I don't know if it's enough, but try with some networks. Figure out, show me a network. So this is an exercise for all of you. Show me a network and it can be a very simple one, where the time complexity for at most one is strictly greater than the time complexity for exactly one. So allowing messages to go faster means that the algorithm is going to be slower. Remember, time complexity is a worst case. So if you allow messages to go faster, maybe on average things are faster, but the worst case is going to be worse. Okay? So that's an exercise for you to do. Have I given you enough intuition? You should maybe try some examples. If you do this exercise by yourself and you succeed, then you will understand what time complexity means. Really, then you will really get it. Okay? So it's actually an important exercise to do, to understand what it means. Any questions on that? Yes?
So the task, the exercise is figure out why with 0 and 1 could actually go faster.
Slower.
I'm sorry, slower.
Yeah, so show me a network. So here's an example. Okay? Show me a network, and for this network, show me that the exactly one has a certain time. Tell me what it is. And the at most one has a time, and tell me what it is. And this one has to be strictly greater than that. So that means, show me a network where if you let the A's or whatever go faster, that the time complexity actually is worse. Okay. So if you allow the messages to go faster, things are getting worse. That's very funny, huh? Okay? So show me a network, that's the exercise, where the at most one time complexity is strictly higher, larger than the exactly one. So it's slower. Huh? Remember, it's a worst case. So maybe there's a lot of executions that are faster, huh? But there's the worst case is worse. Okay? So that's the trick. Huh? Time complexity is the worst case. So the way to do that is to try drawing on a piece of paper. So here's an intuition. The A's determine what are the parents. Okay? So the A's will determine the path that the B's take when they go up, because the B's follow the parents. Okay? So the trick is somehow to make it so that the A's will make really big paths so that the B's are forced to take that path. So for example, and now I'm saying a lot, maybe there's two paths into a node, a short one and a long one. Make sure the short one is slower than the long one with the A's. Now I'm actually almost giving you the answer. I won't say more. Okay? You get some idea how to do it? Some intuition? But work out the details. So this is for you, to really understand the time complexity. Okay?
I'm sorry, but only for A, right? The B is always 1.
That's just my suggestion for you. In this, you can do it by assuming this. You can find a solution by letting the A's be 0 or 1, and then always the B's are exactly 1. But that's just a suggestion for you. There's also other possibilities. I'm giving you some hints so that you can find the answer easier. Okay? So these are the hints. So think about it. Try working it out with some simple ones, and show me an example. So maybe you email me an example before next week's lecture. It's not going to be graded, but it's really important, it's worthwhile for you. If you can show me an example that you find, then you will understand time complexity, okay? You will understand it, like, very strong, intuitive, okay? It's okay for everybody? Okay, so that's the end of this lecture. So remember, we talked about causal order. Define it. We talked about computations. So executions where you move things around, but the causality is preserved they're similar, they're doing the same thing. Each node will see the same events. But the total order is going to be different. So this is called a computation. So computation is an equivalence class of execution. And in order to determine the causality, the vector timestamp is a very important concept. So the Lamport clock is sometimes useful, but the vector clock is really giving you all the information. Okay? So that